All right, so welcome back. We are going to continue with the course material in just a few seconds. I just wanted to touch on a few things. As I said, hopefully technology is going to behave. It didn't during the first class, but we'll go from there. In terms of announcements, I sent out an email last night to everybody, and in that email I just reminded you that you have as resources available to you the teaching assistants and the supplemental instruction and the nucleus tutors. Their schedules are all online and they are available to assist you with the course material and the lab material all the way along. We are not going to have the TA office hours during the week of reading break, so after this Friday it's going to be shut down for a week. They will resume the Friday before class starts. So you have a lab report to do on the Monday, and your term exam is on February 24th. The Sunday teaching assistants will be available to you during that period. So just avail yourself of them. So that was the announcements that I had, and I don't think there was anything else other than, it's pretty cold outside, so try and stay warm. This is where we ended off last day in terms of the course material, and what we are going to do now is we're just going to continue moving forward from this. And so the first thing we're going to do is we're going to look at the reactions and entities in the dissociation of phosphoric acid. So phosphoric acid is triprotic, has 3 protons, and it undergoes a series of dissociations. That's the first proton dissociating. Second proton dissociating. Third proton dissociating. We are going to see in a little bit that we are going to be able to name this as Ka1 for the first proton, Ka2, and Ka3. But for our purposes right now, what I want to do is I want to identify, and I'm just going to make this a little bit smaller, actually. I'm going to get rid of all that. And I'm going to say I want to know what is monoprotic, what is polyprotic, what is monobasic, what is polybasic, what is amphoteric, and conjugate. So that's the answers I want. And I was kind of hoping that you could, in the chat, just type in monoprotic blank, polyprotic blank, and just list the one or more entities that are monoprotic, polyprotic, monobasic, polybasic, etc. And I'm down to 2 bars. Weird. You don't need to start with the monoprotic. You can start with amphoteric. You can start with polybasic. You can do whatever. Just start typing them in, and I will translate them onto the tablet as we go. Thank you. Anyone? HPO4 2- is monoprotic, and he is correct. Polyprotic is things that donate more than one proton. H3PO4 and H2PO4 minus. Correct, Benjamin. Anyone else? In that list, the HCl isn't up there, though. Of the entities present here, what is monobasic? What can only accept one proton? Amphoteric is HPO4 2 minus. Yes, it is. What else on there is amphoteric? H2PO4 minus is amphoteric. Yes. Monobasic is the thing that can only accept one proton, which is H2PO4 minus. And the last one, I'll do conjugate. Polybasics are what? HPO4 2 minus and PO4 3 minus are the polybasic entities. Basically, sorry, bad use of the term, if it's on this side, it is a base. If it is on this side, it is an acid. If it is on both sides, clearly it's amphoteric. It can act as an acid or a base. And of course, and then, yes, we'll just leave it at that. In terms of conjugate, remember the definition of conjugate is things that differentiate through the exchange of a proton. Well, the reactions, exactly how they are written, show that these entities are conjugates of each other because they differ through the exchange of a proton. And so there are all the conjugate entities presented there. Next question is, which is correct, H plus or H3O plus? Through the chat, what is correct, H plus or H3O plus in chemical equations? Benjamin's taking the, safe route and saying both. Neither? Jada, neither? Why do you say neither? Neither. Aren't they the same thing? Lots of good questions. Jada think that they're both partially right, but not 100% right. H3O plus. Most likely in high school you were taught it's H3O plus, it's not H plus. At least that's in Alberta, that's what they're taught. And I've been fighting with Alberta Education for years on that because the correct answer is Jada. Oh, sorry, neither. Neither of those are actually correct. If you think about ions in solution, all ions are actually hydrated. So you have a positive charge or a negative charge, and that attracts the water molecules around it. And we can spectroscopically look at solution and find out that for sodium, there are actually 4 bound water molecules to every sodium ion. Calcium with a 2 plus charge actually has 12 water molecules that are uniquely different from the bulk water that are literally fixed in position around the calcium ion. For the hydrogen ion, it's actually 7 water molecules. So if you want to be absolutely technically correct, you should be writing H H15O7 plus. But that's only valid at 298 Kelvin. This is a temperature dependent phenomena. And so we're not going to write H15O7 plus, just like we don't write NaH2O4. But for some reason, it got into the heads of some people that you can't have H plus in solution, you need to have H3O plus. Well, you actually don't even have H3O plus. So let's look at this reaction, which is simply the dissociation of nitric acid. If you were to be absolutely technically correct, it would be nitric acid plus 16 water molecules to give you H with 7 waters, plus nitrate with 9 waters around it. And then that would actually be only correct at 298. And as you went to higher temperatures, there would be fewer. As you went to lower temperatures, there would be more water molecules surrounding these ions in solution. Or you could just realize that, you know what? I'm just going to write HNO3 goes to H plus NO3 minus, and I realize that aqueous means surrounded by water. Some of those water molecules are bound, as in water has 7, calcium 12, sodium has 4, but the rest of it is just bulk water surrounding these ions. So, in fact, that term aqueous infers the fact that you are dissolved and in water. I'm not going to spend a lot of time looking at the historical acid-base theories. I'm trusting that you have them. Arrhenius is old and outdated, but it said an acid was an H plus donor and a base was an OH minus donor. And that ultimately fails for any nitrogen-based base. So any nitrogen compound is not going to be correctly described by the Arrhenius theory. Along comes the Bronsted-Lowry theory, which says an acid is an H plus donor and a base is an H plus acceptor. That works for any acid and base in aqueous solution, or protic solvents. So it could be methanol, ethanol, liquid ammonia, anything where a proton can come on and off. So the Bronsted-Lowry definition is what we use today to describe aqueous acid-base chemistry. It's perfectly fine. A more general theory that takes it to non-protic solvents, into the gas phase, into electrochemistry, into all realms of science is that of the Lewis definition, which describes an acid as an electron pair acceptor and a base as an electron pair donor. It's the most general theory and applicable to all chemical systems. So that being said, what is the product of an acid-base reaction? Chat or voice, up to you. A salt and a molecular compound, yes. Salt, and it doesn't always need to be water, but it is a salt and a molecular compound. That molecular compound is most often water. If we're dealing with Lewis theory, the product can also more generally be called an adduct. I'm not going to be spending a lot of time on Lewis theory, but we're focusing on acid-base chemistry here. You don't have this slide. I don't know why. It's not absolutely critical. This is just a list of strong acids and bases. So this is a list of strong acids and bases that you should probably know by now. The list of strong acids is on the left-hand side. Strong bases has a diverse array. Most of the acids very clearly have H in them that dissociates completely to give you the hydrogen ion plus the conjugate. Most of those bases give you a hydroxide that dissociates to give you the hydroxide, but there's a few other reactions like metals or oxides, that type of idea, where they react with water. And the reaction with water is a hydrolysis reaction, which we'll talk about in a bit. But first of all, we're going to go and do a demonstration on this, I hope. Just give me a second while I reset the camera. There we go. And because we're going to be working with some chemicals that are fairly noxious, I'm putting on appropriate PPE so that I am safe. This, by the way, is sodium metal. Don't know if you can actually see it in there. I'm actually curious. How good is the webcam to pick that up? You can see, yeah, it's not bad. It's a little blurry. There are chunks inside of there. Those chunks are of sodium metal, and they are suspended or in an oil because sodium metal reacts with oxygen pretty much wherever it can find it. So reacts with oxygen out of the air, reacts with oxygen out of water. And so I'm just going to move my Petri dish out of the way a little bit and grab a piece of this. That is sodium metal. And it looks like whitish. That's not a camera artifact, but it looks whitish because it has reacted with a little bit of oxygen that either dissolves in the paraffin wax, or it was before it was put in there, it reacted with water vapor or oxygen out of the air. I did actually cut this earlier for the earlier class, and you can see that that side is significantly shinier than the other side right there, because that is a freshly exposed piece. Sodium metal is really, really soft. It is pretty much like butter in the morning, not even hard butter. I can take a spatula and I can just shave off a piece of sodium metal like that. I'm going to put the bulk of it back for safety. And what I have here is now a shaving of sodium metal. I'll move back to my Petri dish and set that up. So for this reaction, I'm going to put a little bit of water in there. And in order such that we can visualize it, I'm going to make my solution acidic. And add some indicator. Now, you would only add a few drops of indicator to your titration, but I want to be visualized in the way we go. And so now what we're going to do is, just for the first bit, see what happens when I react sodium with water. So here is a nice little square of sodium, and there it goes. So the pink is, of course, the phenolphthalein trail. The reaction of sodium with water gives you a basic solution. We'll write that up in a few seconds. If you can see it on the camera, there's a little bit of a gas being given off. That gas is ultimately hydrogen, but that's what sodium does when it reacts with water. It ends up, it's actually so hot, while the density is greater than that of water, because this gas is being given off, it doesn't actually have the ability to sink underneath it. It floats on a cushion of the hydrogen gas that is being produced. Now that we've seen the observation in general, let's make a few more. This piece of sodium that I'm going to put in is square. It's kind of a parallelogram component, but it's going to almost instantly turn into a ball because sodium melts at about 411 Kelvin. It actually is going to, the reaction generates enough energy that we get molten sodium floating on the water. There we go. I'm going to do now is I'm just going to add a few drops of oil. The oil that the sodium is stored in is paraffin oil, and it ends up being, protects the sodium from water. It doesn't protect it completely though. As you can see, drop it in, it's going to find a ball and it's going to stop. Do that again, another ball of sodium, and I can help it get out. But now that the water does diffuse into the oil, and so you're not going to be perfectly safe in the oils. And now, of course, they've just fused together, and so we have a large molten ball of sodium floating around. Let's get it off the sides so that it looks cooler. And that is the reaction of sodium metal with water. What is actually happening in terms of chemistry? Is that you have the sodium, which is a solid, is reacting with the water to produce sodium hydroxide, that plus 1/2 hydrogen as a gas. And of course, we know that sodium hydroxide is a strong base, which is giving us the pink color. The other chemical that was there, not on the surface, was that of sodium oxide. Sodium oxide, Na2O, is a salt. And so it's going to dissociate to give you just sodium ions plus the oxide ion. Oxide was also listed as a strong base. As a matter of fact, both the sodium metal and the oxide ion are stronger than that of the solvent. They're stronger than that of water, which means that they are going to react with the solvent to produce the base of the solvent, and that is the leveling effect of strong acids and bases. Any acid or base that is stronger than the solvent is going to react with the solvent. In this case, we have it reacting with water to produce the acid or base of the solvent. And of course, the base of our solvent is sodium hydroxide, or simply just hydroxides right there. And for this one, the sodium hydroxide, the sodiums were originally dissociated in the salt. So we end up getting our basic solution through reaction of the strong base with water, either directly or in a secondary reaction. And I just did that. However, we're more focused on weak acids and the equilibria associated with that. Weak acids and bases, of course, do not dissociate completely in solution. They establish an equilibrium. And we've already talked about the acid and base named reaction or labeled reaction Ka and Kb. The other thing we have is the fact that if HA is a weak acid, then A- also must be weak. It's the conjugate, so it must be a weak base. Similarly, if BOH is a weak base, then B+ has to be a weak acid. And so let's look at the hydrolysis reactions of A- and B+. So we have A minus reacting with water, and this equilibrium is going to reform our acid. It's a conjugate acid-base pair, and what's left over, of course, is hydroxide, which makes sense. If this is a weak base, we should produce a basic solution. Similarly, we have B plus reacting with water, and this should be a weak acid, so this will reform our BOH, and we'll get H plus. So this weak acid is going to produce H plus in solution, which is what needs to happen. If this is a basic reaction, we should have an equilibrium constant that is HAOH minus over A minus. And if we compare that with our KA-KB, you find that this is nothing more than another way of writing the KB reaction. Similarly, the second one, K is BOH, H plus over B plus. This is just another way of writing Ka. So we have now Ka and Kb for the conjugate acid and base. Now, on Blackboard is, in the course resources site, there is a data sheet that's available to you. There's also a formula sheet, but right now I want to talk about the data sheet. That data sheet lists all of the information that you would normally be provided with on an exam. So I expect you to have that available during exams, but also when solving these problems, because it includes the Ka and Kb, or the Ka values of the acids that I'm using. As you're working through problem set 3, I'm expecting you to find Ka values wherever. There's numerous internet resources that list them. The library has access to the CRC. All of those places have where you can find tabulated Ka values, right? Maybe some Kb values as well, or you'll be able to calculate them. Simply, on that data sheet is a list of monoprotic acids and their associated Ka values. The full list is pages upon pages long. This is just a selected list of acids that are commonly used, at least by me, in teaching this class. These are monoprotic acids. These are polyprotic acids. And here we saw for phosphoric acid, there are 3 Ka values for phosphoric acid for each proton as it dissociates off. Ka1, Ka2, Ka3. Carbonic, sulfuric, oxalic acid, all acids that have more than one proton that can dissociate. This is something that you look up. It's not that difficult. If you happen to find a different Ka or Ka value, that's fine. You solve the problem with that Ka value. It's just a realization that different entities, different scientists, when they measure these things, for whatever reason, there's a systematic error in one or both of their experiments. Generally, they're close. Sometimes they're not so close, but generally they are close. So, I'm going to go back to the document camera, and we are going to write the acidic or basic equations that occur with each of the following entities. Sodium hypochlorite, which is just household bleach, sodium chloride, ammonium hypochlorite, and sulfuric acid. So the first one is NaOCl. Stop that. This is a salt, and sodium salt dissociates completely to ions. Then we can start looking at these ions and knowing the strong acids and bases, you realize that sodium is the conjugate to a strong base, and so there's no further reaction with that. However, this is the conjugate to HOCl. This is weak. So OCl minus will hydrolyze in solution to give hypochlorous acid plus hydroxide. And so if we were to dissolve a sodium hypochlorite in solution, we are going to get a basic solution. The next one is sodium chloride. Again, a salt dissociating to give you sodium and chloride ions. And we already saw that there's no reaction from the sodium because it's the conjugate-ish to sodium hydroxide. Similarly, chloride is the conjugate to HCl. And so if HCl is a strong acid, the conjugate doesn't react further with water. So this solution will be neutral. Next on our list was ammonium hypochlorite. And you can see directly that ammonium ion is a weak acid in itself, and this is a weak base. So both of these will react. The ammonium ion going to give that. And the hypochlorite ion we already saw. So this has the potential to be acidic or basic, and at this point we don't know which is going to win out. It ultimately is going to come down to whether the ammonium ion is a stronger acid than the hypochlorite is a stronger base. We will look at that in a little bit once we get into doing calculations. But for now, the solution is going to be acidic or basic. This is an example where we cannot use an ice table to determine the pH of the solution because both of these equilibria are occurring in solution. We need to consider both of these equilibria in order to determine whether the solution is acidic or basic. And right now, we don't have those tools. In an advanced class, we'll look at different methods where we take into account multiple equilibria systems, and we'll be able to figure out whether the solution is acidic or the actual pH of the solution. I can tell you whether it's going to be acidic or basic, but I can't tell you the actual pH. We don't have the ability to calculate that. The last one is H2SO4. And a lot of people will write that this goes to 2H plus SO4 2 minus. That is not correct. Why is that not correct? Through chat or text, please. It's not a liquid, but we're putting in aqueous solution. So I'll be adding water to it, dissolving it in water. So water is going to be added, and we're going to make a dilute solution of sulfuric acid. Why does it not go to 2H plus SO4 2 minus? We saw the answer already with phosphoric acid. Right, because the protons come off, as people have said, and you said, Efren, it's a multi-step reaction. It is a sequential stepwise process. So the first thing that's going to happen is you're going to lose one proton. And that first proton is actually strong. that first proton completely dissociates from sulfuric acid to give you H plus and HSO4 minus. However, that second proton, SO4 minus, is weak. So it's an equilibrium that you need plus SO4 2 minus. Now, clearly the solution is going to be acidic, but if this were being titrated out, you would titrate out all of the initial H plus first, be left with HSO4 minus, and then the HSO4 minus would react, and you'd see the second proton coming off. Oops. I accidentally deleted too much. There we go. So that is the stepwise process that one needs to consider. And if I go back to the data sheet that we had here for sulfuric acid, on the bottom right hand side, H2SO4, Ka1 for the first proton dissociating is much, much greater than 1. Okay, it definitely favors the products to the point where it nears completion. The second proton, Ka2, has a Ka value of 10 to the minus 2. It is weak. There is a Ka value that is less than 1, so it favors HSO4 minus over the SO4 2 minus. So in the second one, the left-hand side is favored. The reactant side is favored. And this leads us into a discussion on relative acid-base strengths. Now, I commented before that at the very beginning we talked about the conjugates. And at the top we have strong acids. Hydrochloric and H2SO4 are strong acids. The conjugate to a strong acid has no basic properties. So the chloride ion has no basic properties, the hydrogen sulfide ion has no basic properties. Conversely, at the very bottom of that table are strong bases, ethoxide and amide ions. The corresponding acids, conjugate acids, have no acidic properties. So ammonia does not act as an acid, ethanol does not act as, try that again. They can't act as further as acids. So the strong, my apologies. The strong bases are on the bottom right. The conjugates do not have any acidic properties. In the middle is a list of weak acids and bases. So between those two lines, everything in there is weak. There's an equilibrium constant associated with each of them. Now, of the weak acids and bases, there is a relative strength associated with them. And if a weak acid is relatively strong, i.e. the high equilibrium constant, the conjugate base is relatively weak in comparison. So their hydrofluoric acid is a relatively strong weak acid. The fluoride ion would be a relatively weak base. And hope that makes some degree of sense. Conversely, we go to the bottom, and you have the carbonate ion being a CO3 2 minus being a relatively strong weak base. The corresponding hydrogen carbonate ion is a relatively weak acid. In the end, the two extremes of weak and strong are the hydroxide ion in the bottom right, and I used H3O plus because it fits better in this table, H3O plus in the top left. The strongest acid you can get is that of the solvent, which is H3O plus. The strongest base is, of course, that of the solvent, which is hydroxide. All right, back to this. What is the relationship between Ka and Kb? You've already seen the acidic and basic reactions involving A minus, so as an acid and base. What is the relationship between Ka and Kb? Anyone? Chat? Discussion? not the inverse of one another. That would infer that if I said 1 over kb, I'd get ka, and I don't. It's not the same. Something with 1 exponent minus 7? No, but something with another number, kind of related to 1 exponent minus 7. Kind of. There we go, from Afrin. The relationship between Ka and Kb is Kw. Now, so we have conjugate acids and bases, and so our expression was H plus A minus over HA, and that was our Ka expression. Then we had HA OH minus over A minus. This was our Kb expression, and if you follow this through, A minus cancels and HA cancels, so what's left when we multiply these things out is H plus OH minus, which is nothing more than Kw. So Ka times Kb is equal to Kw. Now I want to apply that to a polyprotic acid. Presented here are the acidic and basic reactions involving all of the possible ions. I need to figure out what times what equals Kw. So one of the Ka ones and one of the Kb ones multiplied together will give you Kw. What is that relationship? Does anyone, or can anyone see it there? Which Ka times which Kb has everything canceling out to give you Kw? If you look closely, Benjamin said that Kb3 and Ka1, they have the same entities. Ka1 has H3PO4 and H2PO4 minus. Those are present in Kb3. So yes, you are correct, Benjamin. Jason says A2 and B2. And again, they both have H2PO4 minus and HPO4 2 minus. So there's a cancellation there. What's the last one? Ka3 times Kb1. Correct. So there's always a relationship in polyprotic Ka1, Ka2, Ka3, Kb3, Kb2 is equal to Kw. The importance here is that we only ever tabulate the acid dissociation constants. That's all that is ever tabulated, because it is so easy to calculate Kb knowing the appropriate Ka. So all you'll ever see is Ka reactions tabulated, and then you can calculate the Kb for when you need it. Time is it? Oh, I got a few times. Good. Enough time. This is a review of pH. I'm not going to spend a lot of time on it, but we use a logarithmic scales are convenient when the variable changes by several orders of magnitude. So we define a function p, and it is literally the letter p. The p function is negative log of whatever it is applied to. So pH is the one that we see a lot in acid-base chemistry, but we can also calculate pOH as well, negative log of the hydroxide ion concentration. We can calculate the P of any ion concentration. P carbonate is negative log of the carbonate ion concentration. The equilibrium constant also varied by several orders of magnitude, as we saw in the previous tables. So some resources don't tabulate the equilibrium constant, they tabulate the negative log of the equilibrium constant, or the pK value, and that is what ends up being tabulated. And then it is just a matter of calculating the value, taking 10 to the minus whatever. In this example, what time do we got? I actually want to, sure, we will do this. The fluoride concentration in drinking water ranges from 1 to 8, yeah, no, that's going to take a while to do. I want to actually jump to the 2 slides, so I'll come back and we'll do that as an example next day. There's more examples to do. Ignore all this. There we go. This is where I wanted to get to. Just to finish off on a thought experiment, I hope you remember what pennies are. They were in Canada up until recently. But if a penny is 1.5 millimeters thick, how far does 10 to the 14 pennies reach? Does it reach 150 kilometers? Across North America? Around the Earth a few times? The distance from the Earth to the Sun? The diameter of the Milky Way galaxy? Or is it the distance to the Andromeda galaxy? If we had 10 to the 14 pennies all stacked up, how far would that stack go? This is kind of a guess, but William says it goes to the Sun. Are people agreeing with him, or are they going to go a different route? 150 kilometers for Benjamin? I'm sorry, I'm calling these things out. Just type in what you think it might be, and we will finish on this. Why do many people say to the Sun? The people who say to the Sun are correct, but very rarely do I get that many people getting the same answer, because we can imagine it easier. Okay, fine. It is actually about the distance from the Earth to the Sun, which is around 155 million kilometers. That is the distance that a stack of pennies would reach if it were 10 to the 14 pennies would reach. But that's the idea of the magnitude that we are dealing with. From a very thin penny here, which is a pH of 0, which we can easily produce in aqueous solution. To get a pH 0 solution, you just need 1 mole per liter. We'll be doing that calculation next day. To go the other extreme, to get a pH 14 solution, that's just 1 mole per liter sodium hydroxide. So the things that we can do literally in a beaker is the difference between 1 penny and a distance of here to the Sun stack of pennies. And that's where we're going to leave it today. When we come back, we'll go back and do those calculations and continue on with this material. Thank you very much. Have a great day.